In typical fashion, I wish to begin by sharing a personal anecdote that has nothing to do with this chapter. You can skip it, I guess, if you really want to. I want you to know that I've changed all of the names of the people involved in this story just to prevent them from possibly suing me at a future time. Although I'm slightly ashamed to admit it, I was somewhat lazy back in high school. Good grades came with nominal effort, and I wanted to have a more laid-back senior year. As a result, I dropped my last trimester of AP Chemistry, even though I'd earned A's during the first 2 trimesters, and I took social dance. In the short run, social dance paid off more. In the long run, though, I wish I'd stuck with AP Chemistry. Someday I imagine I'll probably contact my old high school chemistry teacher and tell him that now I'm a chemistry professor. Although some of my younger students might not believe it, there was a time prior to the mid-1990s when I was in high school that caller ID didn't exist. During this pre-caller ID era, prank callers could operate with reckless abandon with little fear of being caught. Caller ID more or less ruined the prank calling industry. It's harder to prank call people now without being caught because many people have caller ID, which enables them to know the identities of everyone who calls them. My friend Joe and I came up with a solution to this problem. What if we, the prank callers, call up our randomly selected victims and asked them first if they had caller ID? If they said yes, then we would merely respond by saying, "Thank you very much for your time," and hang up. But if they said no, then we would proceed to prank call them. Usually the prank calls would consist of us making fart noises or something. Would this plan work? Only time and experience would tell. So we called up a few people and got some good responses. "Do you have caller ID, sir?" I would ask. "Why, yes," someone would respond. And I would reply, "Well, thank you, and please enjoy it," and then hang up. But with others we got a different interaction. "Do you have caller ID, sir?" "Why, no." Then I would go, and hang up. Did I mention the fact that while we were engaging in this prank calling escapade, we were doing it during the hours that we had scheduled to study chemistry together? So one night as we sat brooding over our chemistry, the thought came to us, what if we use this prank calling strategy on our AP Chemistry teacher, Mr. James Cullen? So we did. I called him up and asked, "Is this James Cullen?" "Why, yes it is," he responded. "Do you have caller ID, sir?" "Why, no, I don't." Then, and I hung up. The next day, as Joe and I sat in our class making noises, we noticed that Mr. Cullen hadn't come to class yet. For some crazy reason, Joe ran up to Mr. Cullen's dry erase board at the front of the classroom and wrote out the words, "Do you have caller ID? Love, Mike Christiansen." No sooner had Joe finished writing this false message for me than Mr. Cullen entered, viewing it with a displeasurable expression. Upon seeing our teacher enter the room, Joe screamed loudly, "Oh!" threw the dry erase marker into the air, and then ran quickly to his seat. He sat down and pretended that nothing had happened. Now, obviously, Mr. Cullen had seen the entire thing, and he began to glare back and forth between the board and us. We were a little worried that he was going to kill us, but after a few moments of silence, he laughed and complimented us on our funny prank. Well, that night, as Joe and I sat around my room studying chemistry again, Joe came up with another one of his bright ideas. "Hey, Mike," he said, "why don't we do the caller ID prank again?" "Okay," I replied. "Who should we call?" "How about we call James Braun?" Joe suggested. "Okay," I agreed. I should explain that James Braun was a friend of ours from high school who happened to be in our AP Chemistry class. We had told him the entire story, so we knew that if we prank called him, he would know it was us, but we hoped that he would also think it was pretty funny. So I agreed to do it. I grabbed the phone. Joe dictated a phone number to me, and I trustingly dialed it. The following conversation ensued. "Hello," said the woman answering the phone. "Hello, ma'am," I said. "Is James there?" "Yes," she replied. "I'll get him." After a pause, some lumbering, and the sounds of people walking around the house, a man's voice came to the phone. "Hello," he said. "Is this James?" I asked. "Yes," he responded. "Do you have caller I then paused and realized that I recognized the voice of the man I was speaking to. It was Mr. Cullen, our chemistry teacher. "Is this Mr. Cullen?" I asked. "Yes," he answered angrily. "Oh, crap!" I then screamed briefly, "Ah!" and hung up. My friend Joe was sitting over there laughing, of course, knowing that he'd intentionally given me Mr. Cullen's phone number, which worked smoothly because Mr. Cullen had the same first name as our good friend, James Braun. Now, in class the next day, Mr. Cullen laughed after we explained to him exactly what had happened. He also said, "Yeah, I don't have caller ID, but I'm going to get it." I now want to introduce you to a cool reaction called Sharpless epoxidation. It's very useful. In fact, its inventor, Barry Sharpless, won the Nobel Prize for discovering it back in 2001. This reaction might look simple, and it sort of is, but that's part of what makes it so useful. It's simple, yet powerful. The overall reaction works as follows. Our starting material has to be an allyl alcohol, like this one. Remember, an allyl alcohol is an alcohol in which the OH is one carbon away from a carbon-carbon double bond. You'll remember our song, "Allyl, allyl, allyl, al, one away from his pals, ooh!" If we react our allyl alcohol with tert-butyl hydroperoxide and minus DET, we can faithfully, reproducibly, and predictably get a single enantiomer of this epoxide. DET, by the way, stands for diethyl tartrate, which is a diethylated derivative of tartaric acid, a widely available compound found in grapes and bananas. This reaction has its complementary counterpart, for if I treat the same allyl alcohol with tert-butyl hydroperoxide and plus DET, I can get the opposite enantiomer with high fidelity. This reaction, believe it or not, is extremely useful, which brings us back to a principle I introduced to you in Chapter 5. You can't get chirality in a product unless you already have chirality in your starting material or in one of your reagents. I found a recently published synthesis that used Sharpless epoxidation as a key step. In this paper, the Yadav group from the Indian Institute of Chemical Technology synthesized molecule 1 over a number of steps. I hope you can all see that compound 1 is an allyl alcohol. This compound, which contains no stereocenters, was treated with Sharpless epoxidation conditions to furnish molecule 2 in 77% yield with 94% enantiomeric excess. We've talked about enantiomeric excess, or EE, before. To explain, a 94% EE means that 97% of the product mixture formed from this reaction was the enantiomer 2 shown here, and that 3% of the product mixture was the opposite enantiomer. Is this a pretty cool reaction? You bet. Because it enabled these scientists to take molecule 1, which is completely achiral, and convert it with near complete exclusivity into molecule 2, which is chiral. Compound 2, incidentally, was then transformed over various steps into this molecule, amphidenolide T1, an anti-cancer compound isolated from a murine protist. And as I already mentioned, the Sharpless epoxidation is a very useful reaction. In fact, to date, this is one of the few reactions that can be reproducibly done on an industrial scale to introduce chirality into a molecule. Much to your crapulent surprise, I'm sure, we still have a few more oxidation reactions to cover. We now arrive at this one, dihydroxylation of alkenes using osmium tetraoxide. See, if you have an alkene like this, and you treat it with osmium tetraoxide followed by a peroxide quench, you get this type of diol. This diol is called a 1,2-diol or a vicinal diol. It's important to note that the diol product that you get always ends up having the two oxygens being added syn or cis to each other. Thus, if I begin with this starting alkene, cyclohexene, and treat it with osmium tetraoxide followed by peroxide quench, I get this cis 1,2-cyclohexane diol. So you should remember once again that this reaction always gives you the cis 1,2-diol. The mechanism shown here partially is interesting, but I do not require you to know it. Incidentally, I saw a recent episode of J.J. Abrams' sci-fi TV show Fringe that featured an osmium-containing compound that gave certain individuals the ability to fly. Chemically, this is total crap, but entertainmentally, it's pure gold. If you take a 1,2-diol, that's what these kinds of compounds are called, and react it with periodic acid, HiO4, which I like to call HiO4, it actually cuts the bond between these two carbons just like a saw. It then takes the two carbon halves and installs double bonds between each of these two carbons and the oxygen to which they're attached, giving you these products. If you want to know the mechanism, this is sort of how it works, partially. But once again, I don't require you to know it. And here's a sweet example. In this example, you can once again see that we have a 1,2-diol in my starting material. I react it with HiO4. The carbon-carbon bond is severed, and each of these carbons becomes doubly bonded to its adjoining oxygen, giving you this product right here. We can get a similar outcome by using this reaction called ozonolysis. But there's one major difference you should pay attention to here. In an ozonolysis reaction, our starting material is not a 1,2-diol. It's an alkene. Like our HiO4 reaction, however, when we treat this starting material, this alkene, with ozone, O3, followed by a selected workup, the ozone saws this carbon-carbon double bond in half and then installs oxygen on the end of each of these carbons. So once again, we just saw this just like a saw and plop an oxygen doubly bonded to each of these carbon halves, giving these products here. As it turns out, your ozonolysis product can vary depending on which workup condition you choose. If we work up our reaction using zinc and water, or this compound, which is called dimethyl sulfide, then we'll cleave our carbon-carbon double bond and plop, of course, our double bonded oxygens here onto each of the carbon-carbon halves, no sweat, just as I showed you in the previous slide. As I mentioned, you can also quench this reaction with DMS, dimethyl sulfide, and get the same results. The problem is that quenching it with dimethyl sulfide isn't ideal because DMS smells like a monkey's anus. Now, in contrast, if I quench our reaction with peroxide, H2O2, something slightly different happens. You see, during a peroxide quench, if these two carbon atoms have hydrogens on them, and notice I've circled the first one, it does have a hydrogen atom on it, then that hydrogen atom gets converted into an OH in the product. So once again, I saw right between this carbon-carbon double bond, plop an oxygen onto the end, giving me a carbon-oxygen double bond in the product. But one of the H's, or the H here, is converted into an OH. You'll notice that the second carbon has two hydrogens on it. So under these conditions, quenching with H2O2, the product that I get, only one of those two hydrogens gets replaced with an OH. Now I hasten to mention that I don't require you to know the mechanism for this reaction, but if you want to learn it, and it really is cool, I think, then please consult section 20.9 in your book. Now, I think this is a great place for us to do some problems, just to review all of these oxidation reactions. So here you go, my beloved students. I want you to show me how to convert molecule 3 into molecule 4. Once you've done that, then please show me how to convert molecule 5 into molecule 6. Since I'll be showing you the answers on the next slide, I advise you to pause the movie right now and first attempt these on your own prior to moving on. So here are the answers. As we look at this starting material, we want to convert it to this product. It's obvious that the product has a stereocenter that has an oxygen in it. We can see that our starting material is an allyl alcohol. So it should be pretty straightforward that we need to treat this allyl alcohol with Sharpless epoxidation conditions. Now, I'm not going to require you guys to know which an enantiomer or diastereomer of DET to use, minus or plus, in order to get which enantiomer of the epoxide. I just want you guys to memorize that if I take an allyl alcohol and treat it under the proper Sharpless conditions, I can generate either enantiomer of epoxide according to my desires. Now this epoxide still looks different from the product indicated on the previous slide. So what in the world can I do? Well, you'll notice that if the only difference between this epoxide and this product is that I've got a methyl group installed here. How in the world could I take a methyl and put it into that carbon right there? Well, what I could do is if I had a negatively charged CH3, I could do that. What does that mean? Well, it means a Grignard reagent. Give me a Grignard, I've got the equivalent of a negatively charged methyl. This methyl can then come into that position, pump these electrons up onto the oxygen, and give me this product. Now it's very important for you guys to notice the wedges and the dashes here. You'll see that I used my Sharpless epoxidation conditions to install this epoxide in such a way that I got wedges going to this oxygen. In other words, three-dimensionally, that oxygen is coming towards us. When this methyl anion comes in from this Grignard reagent, what side is it going to attack that carbon from? Well, naturally, it's going to attack from the back side, opposite of this oxygen. So that means that this methyl is going to be pointing away from us, or dashed. Once I protonate that, I then get this product. Now there's another detail that deserves attention here. You might ask the question, Mike, why in the world does the methyl attack this carbon in this epoxide instead of attacking this other carbon? You'll see this other carbon here to the left in the epoxide is theoretically attackable by our Grignard reagent. That would give you a completely different product. Why doesn't it attack the carbon to the left? Well, I'm sure you already guessed it. The carbon to the left is a tertiary carbon and is therefore more sterically hindered than this secondary carbon to the right. Therefore, the negatively charged methyl derived from the Grignard reagent will preferentially attack the carbon to the right. Now we'll give you the answer to the second problem. I begin with this starting material, and I've asked you to get this cis, or I should say syn 1,2 diol. How in the world do I make a 1,2 diol with both of the OHs coming the same direction? You guessed it. Osmium tetraoxide followed by peroxide quench. And now we come to some new problems. I want you, my students, to show me how to convert molecule 7 into molecule 8. And once you've done that, please show me how to convert molecule 7 into molecule 9. Once again, since I'll be showing you all the answers on the next slide, I advise you to pause the movie now and first attempt these on your own prior to moving on. So here are our answers. Once again, in the first problem, I want you to take this methylated cyclohexene and convert it into this product. Now you might initially look at this and say, Mike, that product doesn't look anything like the starting material. How in the world am I going to do that? Well, I'd agree with you that initially, upon looking at this product doesn't look anything like the starting material. However, it might help to realize that this product can be redrawn in this way. So you see this molecule over here to the right. You'll notice that this molecule here to the right is exactly the same as this molecule in the middle, our product. All I've done is twisted things around a little bit so that these oxygens are pointing towards each other. Now I've numbered all the carbons in this chain to help you see clearly that these two molecules are exactly the same. Now, I hope you'll agree with me that this molecule all the way to the right does look a little bit closer and a little bit more similar to this starting material. So how in the world can I do that? Well, you guessed it. I need to come up with some way of sawing this carbon-carbon double bond and installing oxygens there. There are two different ways of doing this. The long way is to begin by treating this cyclohexene with osmium tetroxide followed by peroxide quench. That will give you a 1,2 diol in which the two OHs are cis to each other. If I take that compound and treat it with HiO4, what it does is it cuts this carbon-carbon bond and converts each of these carbon-oxygen single bonds into carbon-oxygen double bonds, which indeed is the very product that we're trying to get. The shorter way of doing this conversion is to just take our starting material and treat it with ozone followed by zinc water or dimethyl sulfide. That, once again, cuts, just like a saw, this carbon-carbon double bond and plops oxygens on the ends, giving me this product. Now let's give you the answer to our second problem. How can I convert this cyclohexene to this product shown here to the right? The major difference between this product and the one in the previous problem is that this product has an OH at this position instead of just an H, as we did with the previous one. You might look at this and say, now wait a minute, Mike. This product doesn't look anything like the starting material. I would agree with you superficially, but if you reorient the product to look like this, you can see that it does indeed look closer or more similar to the starting material now. What I need to do is come up with a way of cleaving or sawing this carbon-carbon double bond, plopping oxygens on there, and then somehow getting an OH to appear down here. How in the world can I do that? Well, you might remember that this carbon right here has a hydrogen on it, right? Can I replace the hydrogen with an OH? Yes, I can. If I could, in other words, if I could come up with some way of cutting this double bond and then replacing this hydrogen with an OH and plopping oxygens here, I would get my product. And as I showed a few slides ago, this can be done by doing ozonolysis, and instead of quenching with zinc, water, or dimethyl sulfide, quenching with hydrogen peroxide. Remember, hydrogen peroxide replaces any hydrogen that's stuck to the alkene carbon with an OH. Can we use the reactions we've learned in Chapter 20 to do total synthesis? As you're likely now accustomed, I'll be giving you the chance to test your mettle on the field of synthetic battle in class. In the meantime, though, don't be shy about attempting some of the synthesis problems from your text on your own. And now we finish. The day is old. We've had our fun. Tomorrow is another one. From near to far, from here to there, funny things are everywhere.